All right, this is problem number 33, and the question reads, what value of a makes our function f of x equals x squared plus a over x have, and part A is a local minimum at x equals 2, and then part B is a point of inflection at x equals 1. And the first thing to note about this problem is part A and part B are independent, so we're not trying to have a min at 2 and an inflection at 1. We want to do part A, and then independently, we're going to do part B. Okay, so part A, we want a local minimum at x equals 2. To get a minimum, we're talking about critical points. You know, a critical point is where the derivative is 0 or undefined. So let's start by taking the derivative of the function. So f prime of x squared gives us 2x. And then we have a over x. A is a constant, so we get minus, because it's x to the negative 1, so we get minus a over x squared. Okay, we would like this derivative to be 0 or undefined to have a critical point, because we know there's mins and maxes at critical points or at endpoints. We're not talking about endpoints for this function, and so we're looking for the critical points. So our derivative, we set it equal to 0. There's no value of a you can choose that will make our function undefined at 2. So we have our derivative equal to 0. And we know we want it equal to 0 when x equals 2, because we have a minimum, look at this, at x equals 2. So let's take our derivative at 2. I'll sub in the 2. And we want that to be a critical point. So when x is 2, we want our derivative to be 0. So I'll simplify a little bit. I'll solve this. And it looks like a will have to be 16. Now, a question you might have is, wait a minute, how do we know that's not a max? As a critical point, is that a max or is that a min? And so let's just check and see if we've done this correctly. And if not, we're kind of out of luck. But let's take the second derivative and use our second derivative test. And so now our 2x becomes 2, and our minus a over x squared becomes plus 2a over x to the third. We've got a is 16. So let's see at 2, we've got 2 plus 2, we've got a 16 in there. And our x is 2 to the third. So it looks like 2 plus 32 over 8. It looks like 6. Our second derivative at 2 is positive. So by the second derivative test, that means x equals 2 truly is a min by our second derivative test. So that completes part A. Now we're going to do part B. And again, understanding part B, as we're doing it, it's independent from part A. So we'll switch to a new page here, remind ourselves what the function was. F of x equals x squared plus a over x. So here's part B. F of x equals x squared plus a over x. And the idea is the same idea. We now want to find an inflection point. So looking for inflection. We want that inflection point when x equals 1 this time. So you remember inflection involves the second derivative. And even though we just did those, it doesn't hurt to do the derivatives again. We have 2x minus a over x squared. And our second derivative will become 2. And then we've got plus 2a over x to the third is our second derivative. Now, for an inflection point, a possible inflection point at least, we would like our second derivative to equal 0. And we'd like it to equal 0 when x equals, look right here, when x equals 1. So I'll sub in 1 for x. So we get 2 plus 2a over 1 cubed. And I'd like that second derivative to equal 0. So solving this, I get 2 plus 2a equals 0. Or solving it, I can see a will equal negative 1. Just like part A, we should check that and make sure that truly is an inflection point. There is no derivative test to tell this other than, sorry about that, we'll start with x, values of x. We'll look and see, does our function really change concavity at when x is 1, when I have a negative 1 in for a. So when my function becomes, f of x becomes x squared, and a is negative 1, minus 1 over x. Or when my second derivative becomes 2 plus a negative 2 over x cubed. So let's see, does the concavity really change at 1? So let's try before 1, and let's try after 1. Before 1, I choose a value, not 0, will I? Because it's not defined at 0. So let's choose a value about a half. And if I try my second derivative with a value of 1/2 in there, I've got 2 minus 2 over 1/2 cubed. 1/2 cubed is an 1/8. I bring that up on top. I get 2 minus 16. I'm getting a negative. So my second derivative is negative. I know my function is concave down. Let's try a value bigger. Now, between 1 and infinity, such as 2. I'll take my second derivative at 2. So I get 2 minus 2 over 2 cubed. 2 cubed is 8. I get 2 minus a fourth, which is 1 3/4, which is positive. So when I look at my second derivative, I notice that the second derivative at 1, it changes from negative to positive. So this truly is a point of inflection. So we have an inflection point at x equals 1 because the second derivative switches signs. That completes our problem.